Hello, welcome to another coding challenge. In this coding challenge, I'm going to, with great trepidation but excitement and energy, I'm going to program from scratch the Mandelbrot set, show you how to do it, talk about the math behind it, and make it happen in JavaScript in the browser. Problems will come up, but I'm going to do my best. So why do you care about this? It's a fractal pattern. You can make some beautiful images with it. You might also just sort of learn a bit about programming and pixels and arrays. But yeah, so I don't know, you're here, you probably want to do the Mandelbrot set. If you don't, you can go outside and play Frisbee. So let's see. Now, let's look at least and let's read this definition, which, you know, is going to cause a small, like a slight pain in my side here to read it, but I'm going to do it anyway and try to unpack and understand it as best we can in the context of a short YouTube coding challenge video. Okay, the Mandelbrot set is the set of complex numbers C. Okay, what does it mean for something to be a complex number and then to have a set of complex numbers? That's a question we need to answer. Which the function f of z equals z squared plus c, okay, what does that function mean exactly? Does not diverge. What does it mean for something to not diverge? When iterated from z equals 0. Okay, so there's a lot of stuff in there. And the first thing I want to do before I start writing the code is just talk about the math. And the first thing I want to do is talk about what is a complex number. Okay, so you might be familiar with an operation in math called square root. I could say, oh, I think I have the wrong end of this pen. I could say the square root of 4. By the way, I forgot this whole thing. I was practicing pronunciation, and I completely forgot to do it. The Mandelbrot set is named for the French mathematician Benoit Mandelbrot. Okay. I spent all this time practicing to say Benoit. Okay, the square root of 4 is 2. The square root of 16 is 4. The square root of -1 is what? Well, in fact, you might say to yourself, there is no such thing as the square root of -1. It's impossible. Any number squared, positive or negative, results in a positive number. So the square root of a negative number inherently does not exist. This is not exactly the case. In fact, there is an answer to this, and it's called I. And I is an imaginary number. It's imaginary because it's not a real number. It doesn't actually exist, but if we consider the square root of -1 actually be something that does exist and call it I, all sorts of magic can happen. One of which, by the way, is the Mandelbrot set. So this is what's known. So this is a real number, and this is an imaginary number. If I put those two things together, 3 plus I, this is a complex number. A complex number has both a real component and an imaginary component, and it is typically written in the form A plus BI. A is the quote-unquote real component. B is the quote-unquote imaginary component. I personally love imaginary numbers because I could just imagine them and use my creative imagination to think about imaginary numbers. Okay, so this is what a complex number is. Now let's go back to that definition. The set of complex numbers. Okay, what does it mean for something to be a set of complex numbers? Well, this actually relates to, you can think about a canvas, right? A canvas, our canvas, the thing that lives in the browser in HTML or processing or Java or whatever graphics environment you're using, has an x-axis and a y-axis. It's a two-dimensional plane. Well, what if A, and I don't know which one should be which, but I'll just pick one and hopefully the Mandelbrot set won't be upside down. A, let's say A is the x-axis and B is the y-axis. The plane of complex numbers, the set of complex numbers, is all and a number that appears here might have an A value of 7 and a B value of 3, meaning 7 plus 3i. So this plane, this set of complex numbers, is all the complex numbers for all A possibilities and all B possibilities. So we have to do something for every single set of complex numbers within the sort of bounds of this canvas. Okay, so that's good. Which the function f of z equals z squared plus c does not diverge when iterated from z equals 0. Okay, this is probably the hardest part for us to understand, but once we understand it, we're done and we can actually start to program the code. So let me come back over here and let's write that. So f of z equals z. I wrote the wrong thing down. I might need some more space. Let's see. Z squared plus C. Now, C is a complex number. A plus bi, any number from this spot. And we want to iterate this function starting with z equals 0. So if we start with z equal to 0, what do we get? Well, z, the next z, like of z, like we're z1, if this is z index, z sub 0, z of the 0 generation, z of the first generation equals z squared plus c, which is, by the way, just c. So now z sub 2 equals what? C squared plus c. And z sub 3 is going to be c squared plus c. So one of the things we need to look at how to do here is how do we get c squared? This is where I need a little bit more room. C squared. What is c squared? C squared is a plus bi times a plus bi, right? Because c is a complex number. It has a real component and an imaginary component, a plus bi. Well, let's multiply these two things together. A times a is a squared plus a times bi plus a bi. Now, bi times a plus a bi again. Bi times bi. Now, this is a crazy one. Bi times bi is what? B squared, I squared. What's I? I is the square root of -1. I mean, it's imaginary, but it is the square root of -1. So if you square it, what do you get? -1. So this actually turns out to be a squared plus, this is abi plus 2abi plus, oh no, not plus, minus, because I squared is -1, minus b squared. Or we could look at this another way. A squared minus b squared plus 2abi. Well, guess what? This is a complex number. It has a real component, a squared minus b squared, and it has an imaginary component, 2ab. So this is all the math that we need, because what we're going to do is actually in our code just calculate these values over and over and over again, generation to generation. We're going to iterate. And as we calculate those values over and over again, we need to see, do they remain bound in an absolute value? So the question is, are they tending to go towards infinity, or are they actually just like staying around some reasonable number? And the Mandelbrot set is the set of numbers for which the function remains bounded. So it's all the time, for all of the possibilities, it's all of the ones that don't tend towards infinity. Whew, that was a lot to think about. Maybe pause this video and go outside, take a break for a little while. But now if you're back, I'm going to start writing the code for that, and I'm going to refer back to this math a couple times, probably. I don't know if you're following this. I'm having a good time. OK, so let's go to the code. Now, I have a sort of empty P5.js sketch here. This is some JavaScript code. It's just like a basic skeleton here. The only thing that it's doing is it's looking at every single x value and every single y value and setting its pixel to a grayscale value of 51. So I'm going to go take a look at that. It's right here. You can see here. There we go. There's my gray window. If I were to change this component to 255, you can see it's like a redder window because I added more red. So what I need to do ultimately is, I need to, inside this code, for every one of these x and y values, I need to run this Mandelbrot set f of z, z squared plus c math thing, and I need to see, are my numbers getting bigger or are they not getting bigger? And then I'm going to set a color based on that. OK, so now we have an interesting question, though, to ask, which is, if this is my pixel window, which goes from 0 to 360 and 0 to 240, well, do I really want, and a complex number is a plus bi, or do I really want to deal with complex numbers like 357 plus 212i? No, I really want my range. I don't know what it should be, but I'm going to just go between -2 and 2, and then let's try that. Top to bottom, and probably something's going to be squished, but it'll be fine. So the first thing I need to do is I need to figure out what are my a and b values relative to x and y? So I want to map x, which goes from 0 to width, to maybe between -2 and 2. Let's make this a square, and then I don't have to worry about any of this nonsense. And then I'm going to map b, and this is really, which goes from y, which goes from 0 to height, also between -2 and 2. So I'm looking for all the complex numbers that go between -2a plus -2b. No, sorry. -2 minus 2i all the way to 2 plus 2i. That's the full range. Okay, so I want to use those numbers. Now, I need to start doing that iterating. Okay, so the first thing I need to do is say, I know how to do this. I've done this before. Okay, let's look at this. We need to over and over again. So we need to over and over. We need an operation that's going to happen over and over again. So let's keep track of how. One thing we should do is keep track of how often are we doing this. Let's have a variable called n, because I want to just make sure, like, as long as n is less than, I don't know, some arbitrary amount, 100. Like, I don't want to iterate more than 100 times. I can keep doing what I'm doing, and I want to have z start with something. So I'm going to have z start with 0. I'm sure I'm getting something wrong here because I'm like thinking about this as I'm doing, and I'm going to fix it as I go. But let's figure out some things I need to calculate. I kind of want to like pause recording and go look at my code from before. Okay, but it's okay. I'm fine. I'm fine. It's going to be okay. Okay, did I get something wrong in the chat? Everybody put like rainbow emojis or something if I did something horribly wrong. Or maybe rainbow, maybe that's not right. It should be rainbow if it's correct. Okay, so the first thing I want to do is I want to calculate a squared minus b squared. Okay, so I'm going to call that AA. Is or let's that's going to be my new a. Is a times a minus b times b, and then I also need to calculate 2ab. So I'm going to call that bb is 2 times a times b. So I have now calculated the real components, the real and the complex components for the next generation. And then what do I need to say? I need to say a equals AA and b equals bb, and do it again. So this is just my iterative process, because I start with, I think this is right? The number while, yeah. Oh, and then I need to say n plus plus. Okay, now, another thing I could do here is I could say, like, what does it mean for this to be unbounded, to tend towards infinity? What if I just say something like, I could be really lazy. What if AA plus BB is greater than, I don't know, 16? Or I made up that number. That means maybe, and I want to take the absolute value of that. What if the absolute value of those two, the real and the imaginary component added together, goes toward infinity? Greater than 16, that's my infinity. Then I want to break out of it. So the question is, did I get to 100 or did I not? So look, so this is, I should have thought about it. I'm going to come back. Maybe we'll talk about this again. Let's see how far I've gotten. Why not use a for loop? Well, I could use a for loop. That would make a lot of sense. But I'm just using a while loop for no good reason. Okay, so now let's just do something. I'm just going to say, like, now, if n equals 100, right? If we got to the max iterations, and I should probably make that a variable, then let's make a brightness value. Brightness value equals 0, and then brightness value equals 255. So let's just see what happens now if I basically, with this simple little algorithm, figure out whether n kept going and remained bounded, or if it went to infinity. Let's see. We should get something. Ooh, I got a nice like circle. That's promising. So now let's be a little bit more thoughtful about this. Maybe we can do some sort of coloring based on the value of n. Maybe that will get us something better. So let's actually say now, map n, which could go from 0 to 100 between 0 and 255. What did I do wrong? Time out! Okay, welcome back. There was a critical error in what I had written here, which I just I didn't notice, and thankfully the internet chat came to the rescue. And it's right here in these lines: A equals AA plus A, B equals BB plus B. Now let's think about what's going on here. If you recall, the idea of what we're doing is we're saying Z, the new Z, equals the previous Z squared plus C. And all of the math that I did here, all of this right here, this is me figuring out what Z squared is. Z squared is AA plus BBI. That's what Z squared is. So what do I need to do? I need to then add to that C. But C is always the core original real and imaginary component of where we are in this complex plane. So even though I want the new A and B that's then going to get squared for the next iteration to get updated, right? I want the new A and B that's going to get squared over and over to get updated. This that's getting added to it, C, this is really what's standing in for C right here. This has to be those original values. So I'm gonna just do this. I'm going to say CA equals A. And maybe somebody on the internet here can, I'm going to post this code to GitHub, can submit a pull request with nice variable namings for all this stuff. Because I feel like, boy, this is like, I have a pet peeve, and I'm really doing my own pet peeve, which is like all these cryptic variable names that would never make any sense if you were just coming to look at it. But it is what it is right now. So I need to store those original values and keep those as CA and CB. So let's take a look now and see what we get. Ah, this is starting to look like that Mandelbrot set. You can see it there. Now you can see like, oh, I kind of like, it's not exactly centered. I'm in sort of the wrong place. So, you know, we can futz with that. One way we could futz with that, we could say like, oh, let's kind of like have a little bit of a wider range. Oh, and you can see I kind of like squished it. So I'm going to make Y the same. There you go. But it's also still doesn't really look exactly like what you think of when you think of the Mandelbrot set. You know, if I zoom in, you can see there's some level of grayscale there. What I'm doing is I'm essentially saying, let me just take the number of iterations it got to, right? If it got to 100, it's done. The number of iterations before it breaks out and gets to, if it goes to infinity, how many iterations did it take for it to go to infinity? So first of all, one thing I should say that if n equals 100, and this is driving me crazy, I really just need a variable here, which is I'm going to call max iterations, and I'm going to set that equal to 100. Because I hate that I'm typing this everywhere, so I'm going to put this here, I'm going to put this here, and I'm going to put this here. So now, if n actually gets to max iterations, let's say the brightness is 0. And now you can sort of see like, ah, look, it's all black in the center, and then there's some white kind of on the outside. And there's so many different ways you could color stuff. Here's one way. I'd use this sort of mapping way. Another thing that I could do is I can say n times 16. And I can say modulus 255. So I recycle back down to 0, and you can see, oh, that looks kind of interesting. I don't know what good that did, and maybe I need to floor that for it to look like what I want it to look like. Boy, I thought this was how I colored it in a previous thing. Welcome back. That was an awkward cut, but so what? I was having some trouble figuring out how to color the Mandelbrot set, so I think what would be best to look at first, actually, is just to completely simplify things. So this is what the Mandelbrot set looks like if there's only two possible colors. If there is essentially a background color and a foreground color. The background color is set to be 200. So every pixel is 200 unless it's a pixel that's made it all the way to the max iterations. That's something that's bounded. That's within the Mandelbrot set. So if it's within the Mandelbrot set, its brightness is 0. It's a black pixel. Otherwise, its brightness is 200 so we can see it. So what I want to do is keep that core Mandelbrot set, the set itself, with a pixel value of 0. And now you could probably Google Mandelbrot set color system, and you could probably find all sorts of ways of doing it, but thankfully the internet chat came to my rescue, and let's just look at one other way of coloring this particular fractal. So what I'm going to do is, what I want to do is say, okay, well, the iterations got somewhere between 0 and 100. So I'm going to map. I'm going to speak a little bit quieter now because I think there's a session going on in the next room. I'm going to map the number of iterations from 0 to max iterations, and I'm going to make that some brightness value between 0 and 255. Let's look at that. Yeah, it kind of worked, but you can barely see what's going on there at the edges. So we need a way of changing the kind of scale here. And actually, a better way of doing this would be to actually first just normalize n, which goes somewhere between 0 and max iterations. Normalize that between a value of 0 and 1. And then I'm going to say bright equals map the square root of that value, which also incidentally has a range between 0 and 1 to between 0 and 255. So if I do that, and I refresh this page, now you can see this is starting to look more like what you might be used to seeing in a kind of Mandelbrot set visualization. And the other thing you'll notice here is I'm just sort of looking at this zoomed out version of the Mandelbrot set. The reason why it's zoomed out is because the minimum and maximum range here are between negative 2.5 and 2.5. So what if I went between negative 1.5 and 1.5? Come on. Now you can see I'm kind of zoomed in on it. And what if I went between negative 0.5 and 0.5? And by the way, what if I just made these variables? So what if I said min x equals a negative 0.5, min y equals, and actually I'm going to say min val is negative 0.5 and max val is 0.5. And what I'm actually going to do is let's make a min slider. Oh, I can't do that up here. And a max slider. Min slider equals create slider. Now I need the minimum value to be some value between like, I don't know, negative 2.5 and 0. And I'm going to start with negative 2.5 and have a range of increment value of 0.01. And the max value, this is kind of silly what I'm doing, how I'm doing this, but max value is going to be the same, but between 0 and 2.5. And we'll start at 2.5. And then what I'm going to do is actually say min slider dot value, max slider dot value. And I'm going to do this now for A and B. Now I'm going to map Y as well. So now I have two sliders. So if I run this program, whoops, create sliders not defined. OK, I forgot to include the P5 DOM library. So let me include that P5 DOM library. And you can see, OK, there's some sliders down here now. Now, there's sort of an issue, which is that I'm changing the sliders, but I'm not seeing anything change. So let's figure out what's going on here. It is at negative 1.5. Oh, I have no loop in my code. Because in draw, before I didn't want it to change, so I just had no loop. So I'm going to take out no loop so that it loops. But there really is another issue, which is that, you know, I can make these changes, but look how slow. So this pixel operations are really, really slow. So I'm going to do this I'm going to make like a 100 by 100. Oh, the other reason why it's so slow is I made this ridiculous 1,000 max iterations, meaning for every pixel it's going to iterate 1,000 times. So that's terrible. I don't need, let's just do it like 50 times. And now you can see, like I can start to zoom in to different parts of the fractal. It's actually quite fast. So now we can see like, well, maybe I should let it be a little bit bigger. And maybe I should let the maximum iterations be 100. And yeah, it's still kind of like at a reasonable speed. And you can see I can start to zoom in and we can really get the sense of the fractal, this idea of a fractal of the entire shape of the Mandelbrot set. There it is up there. I can't reach up there because my hands get cut off. But you see the idea. I don't know if you can still hear me. I'm speaking quietly. This has been kind of a crazy video, but hopefully you got something out of this. Talked a little bit about complex numbers, imaginary numbers, looked at how to set pixels according to what the properties of iterating those numbers happen over a plane of x, y values, and looked at a little bit of how we can manipulate it with sliders. And what I would love to see from you, if you watch this video and want to make something with it, look at the code, think of a more thoughtful way of adjusting the range, of doing a zoom, a more thoughtful way of coloring, a more thoughtful way of exploring what this algorithm can do. And in the next video someday, I will not make this till next week, I'm going to look at what it means to create something called the Julia set, which are little fractal patterns that are kind of like leaves or branches coming off of the Mandelbrot set. And we'll look at those in the next fractal Mandelbrot Julia set coding challenge video. Thanks for watching.